Now, when Haber noticed his reactions appeared to stop, what he was able to do was take a look at the product and reactant concentrations at that time and employ what we knew about chemical equilibrium to determine a rate constant, an equilibrium constant for that reaction. So when you're given a series of experiments, and it doesn't matter what your initial concentrations are here, you can see I've got 5 experiments with varying concentrations of products and reactants. In some cases where I have a little bit of both. And what we see after some amount of time is that the concentration of both those stop changing. And so we can write the equilibrium expression for this reaction as such that K equals NO2 squared over N2O4. And now what we can do is take any one of these experiments and their concentrations at equilibrium and plug them into this expression. So I will pick on the 5th one. So the NO2 concentration is 0.0141 quantity squared all over 0.0429, and going through and solving for that, I get 4.6 times 10 to the minus third. And so if you're at equilibrium, then for any one of these experiments we should get an equilibrium constant of 4.6 times 10 to the minus third. And we see we do when we do that. We see a little bit of deviation in the very last significant figure there on that table, but that's because these are experimental measurements and there's always a little bit of uncertainty in an experiment. But we can confidently say the equilibrium constant is 4.6 times 10 to the minus third.